This is Neil from Anabit, and welcome to using the two-point calibration method to increase your ADC or analog to digital converters measurement accuracy. And before I get started, I'll just mention, please subscribe to the Anabit YouTube channel. If you like this video, please hit the thumbs up. Check us out on Instagram, and if you go to anabit.co and enter your email address, you can get updates whenever we come out with new blog content on our website, new video on YouTube, and also when we come out with any new open source data converter products. All right, let's get started. Okay, here's the agenda for what we're going to cover in the video. First, we're going to start out by going over gain and offset error in your ADC circuit. And the reason we want to go over gain and offset error is because those are the type of errors that the two-point calibration method corrects for. And the reason I say ADC circuit is maybe you're just calibrating your ADC, you're connected directly to it. Or maybe your ADC has a op-amp buffer driver, maybe it has an active anti-aliasing filter on the front. Well, those op-amps are also going to have gain and offset error. So this two-point calibration method corrects for gain and offset error in your analog path all the way to your ADC and including your ADC. Second, we're going to review the math behind the two-point calibration method, right? So the two-point calibration method is targeting gain and offset error, which is static error, and it's linear in nature if we look at it across the ADC's voltage range. So that's the math behind it that we'll review in detail. And then we'll look at the two-point calibration method, just kind of go over it step by step, including some tips for each step. Then we'll look at it in action. So we'll look at a demo using the two-point calibration method, and we'll use one of Anabit's open source ADC reference designs. The range right ADC is what we'll use in the demo. And then from there, we'll look at how we implemented this two-point calibration method in embedded code. And we'll use Arduino code as our example. And then the sketch that I use for the demo and that we go over will be available on GitHub if you want to check it out there. Okay, here is a two-dimensional chart of an ADC's input and output codes. And the idea here is this is a 4-bit ADC, right? We use a 4-bit just for simplicity's sake. And so it's going to have 16 different quantization levels, right? So on the x-axis, we have the input code or the input voltage that is measured as a code, and then we have the output code. We see these steps. These are the different quantization levels, and the blue line represents the ideal situation where there's no error. There's no gain, no offset error. So what happens here is whatever the input code is, 10, we'll get 10 out on the output code. Real ADCs are going to have error, and they're going to have gain and offset error. And often these are the most dominant types of error for the ADC, especially for DC measurements. So for gain error, that's shown in the orange line. For gain error, that basically starts at the same point, but then starts to deviate. And it starts to deviate because it has a different linear slope than the ideal curve, right? So that's what we need to correct for, is that different slope for gain error. And then for offset error is a static error that's always there, constant along the ideal curve. If we assume that these are our only static errors and we do this two-point calibration, the only thing you're left with then is the quantization error. And if you're not familiar with quantization error, go to the anabit.co data converter U blog where you can find a tutorial on quantization error. Now, of course, there's other error sources. A lot of them, though, are more noise-based. So this is not going to correct for noise, whether that's high-frequency noise or power line noise or noise caused by a switching power supply, but this will correct for the static linear errors. Okay, and the math behind the two-point calibration method. So this is going to use the slope-intercept formulas that you learned in algebra, along with a lot of the variants of the slope-intercept formula. If you want to learn more about the slope-intercept formula, I'll have a link to some more details on it. But basically it says y equals m times x plus b. And y is the point that we want to correct to. X is our actual measured value. M is going to be our gain error. So M will be our gain correction factor, and B is going to be our offset voltage correction factor. So let's step through an example. So let's say we have an ADC that has a voltage range of 0 to 5 volts. So what we need to do the two-point calibration is we need 4 voltage values. We need to pick 2 points on our voltage range. Ideally, the 2 points are spaced out from each other. So let's say we pick 10% and 90% of our range. So for 0 to 5 volts, that would be 0.5 volts and that would be 4.5 volts. So now we have two of our voltage values, our actual voltage values, 0.5 volts, 4.5 volts. Then we have to take those values and measure them with our ADC before we do the calibration. So what does the ADC actually measure when an input of 0.5 volts is there? What does the ADC actually measure when there's an input of 4.5 volts there? From those values, and we can see them right here, we have V high actual, V low actual, V high measured, and V low measured. We can do a simple equation to get the gain correction factor. And then once we have that gain correction factor, we can then calculate the offset correction factor. So this would be our gain correction factor times our measured low value minus our measured low actual value. And now we have our offset correction, right? So then once we have these, and we only have to calculate these once, right? So we do this calibration, we can store this information in our code. Then every time we make a voltage measurement, we take the measured value, we apply the gain correction plus the offset correction to get our calibrated voltage. Before we get to the demo, let's just step through the process because there is some other things during the process you should be aware of. We want to establish a voltage source or some type of reference measurement to establish what is our actual calibration voltage. So maybe you have a really accurate voltage source, you can feed it right into your ADC, set it for different values. Or maybe you have a stable voltage source that you then can measure with a highly accurate voltmeter to then get your actual voltage value that your ADC is measuring. And that's what I'm going to use in my demo. And if you don't have access to a highly accurate voltmeter or a highly accurate voltage source, you can also use voltage reference ICs, right? So you could buy off-the-shelf reference ICs with high accuracy, and you can use those for your points in your calibration. Or you can use a single voltage reference and then precision resistor divider networks to get two different accurate voltage values to calibrate your ADC, right? But that's important, is you want to make sure you're starting from a point that's much more accurate than the ADC circuit you're trying to calibrate. One thing you want to make sure you do too is allow your devices to warm up, your calibration devices as well as your ADC circuit, right? Every IC out there has some type of temperature drift spec. So the reason is when you first power everything on, no current was flowing in your circuit. All of a sudden, current's flowing. The temperature in the circuit starts to change a little bit. So you want to let that stabilize during that warm-up time. And you want to do the calibration in a temperature range that you're going to use that ADC circuit in. And then we want to measure 2 points. And I mentioned this already. Ideally, you want to pick about 10% and 90%. That way you get nice spread out points along the ADC's range that's not at extremes, right? You don't want to go to the one of the extremes because there might not be any gain error there. So 10, 90%, or approximately 10 or 90% are great rules of thumbs for doing the calibration. Next, you want to calculate the gain and offset error. And this is something you only need to do once. You can store it in software and then retrieve those values. And then every time you make an ADC measurement, you apply those values. Another thing I'll mention is you can correct either the codes or the voltage, right? In my demo, I'm going to correct the voltage. So I'm going to take these ADC codes, convert them to a voltage, then do the correction. But you can do it either way. I go right to voltage because that way I'm correcting floats instead of dealing with converting integer values. Okay, let's see this process in action. Okay, here's a little video of the demo. We're looking at Anabit's range right open source ADC design. This one has an 18-bit ADC plus a front end that allows you to adjust the input voltage range. That's why it's called range right. And the idea is the range right can have various different input voltage ranges. This one for this demo is set up for plus 12.3 volts to negative 12.3 volts. So a range of over 24 volts. And we're going to pick values of 10 volts and negative 10 volts as our 10 and 90% points. We have a stable voltage source connected to the input. Then we have a high accuracy voltmeter measuring it to get our actual voltage value. And then I have an Arduino Nano Every using SPI communication that's communicating with it and setting these values and doing the correction factors and things like that. Let's see the actual value that's being fed to the ADC for our first calibration. So we have 10 volts. So I have my DC source set to 10 volts. this high accuracy voltmeter is telling me it's not actually 10 volts. It's 10 volts and 2.7 millivolts. And I'm only going to calibrate to the nearest hundredths of microvolts. So that is our actual voltage value for one of our calibration points. We're looking at this is a serial output from the Arduino Nano Every that's connecting and controlling the ADC. So right now, there's no calibration applied, and these are our actual measurements from the ADC. And you can see we're getting about 10.44, 10.45. I'm saying 10 point, but it's 10.0045. So we can see that this is almost about 2 millivolts higher than the measurement we saw on the voltmeter. So we're going to call this 10.0045, and we're going to go up to the code, and we'll go over this code in more detail, and we're going to enter it in. Now, I've already done it. We have the negative 10 volts actual and measured, and I didn't show that in the video. I just did that outside because there's no point in showing both of them. And then here's the values we just saw, and I've already entered them in here, right? So here's what we saw on the voltmeter, and here's what we saw on the reading from the ADC. Now, what I have in here is I have a way to turn on and off the calibration. So now that I have my readings, my correction values, I want to turn on the calibration. So we're going to do that here. I have a constant in here, and 0 means don't do 2-point cal. Now I'm going to change it to 1 because I have my calibration points, so I can do the calibration. So I'm going to set that to 1. We're now going to upload that code to the Nano Every that's controlling our ADC, and we're going to see that happen. Okay, and then I'm going to reset the serial monitor, and we see our code start up, and we now see our new reading that I'll let a couple more readings populate. So when the setup code for the Arduino setup function runs, we do these calculations. In my code, I call it the slope. I know in this tutorial I call it gain, but this is the gain correction factor, and this is the offset correction factor. But we can see the slope is less than 1, so that must mean the error slope is greater than 1, so our correction factor is pulling it less than 1 to make it 1. And then our offset error is actually positive, and so our correction factor is negative. We're using that point slope intercept formula with these values to now get these readings that you're seeing. And remember what the voltmeter was reading. It was reading 10.0027. And so now that's approximately what we're seeing here. Earlier, the ADC, I think, was measuring 10.0045. So we can see the DMM is still measuring the same value, right? So now we went from being almost 2 millivolts different to now just being a handful of hundreds of microvolts different. So we can see multiple orders of magnitude correction factor in the accuracy of the ADC. Now, what I'm going to do next is I'm going to change the source to 5 volts. So I just changed our source to 5 volts so we can kind of see it for a different voltage value. And we can see our ADC with the 2-point calibration applied is getting about 5.0019, or about 5 volts and 2 millivolts is what I should say. So we see that print out a couple times. Now we go to our DMM, and we can see, lo and behold, it's getting basically the same value, where we only have a difference of tens of microvolts difference. So that's where you can see this calibration method in action, and you can see it working here. Now let's look at the code we use to implement this. Okay, now we're looking at the Arduino code, and I'm not going to go through the whole sketch. You can, once again, access this on GitHub, but I am going to go through parts that are related to the 2-point calibration. So here's the define or constant variable we use to turn on and off the cal. Remember I said we want to average readings together when we do the cal, so we're trying to cancel out noise. So that's what this is doing. We're averaging 12 readings together. Here are our 4 voltage values, our 2 actual and 2 measured, which you saw in the video. These are our global variables for holding the correction factors, the slope or the gain and the offset. So right now they're just set for ideal, but they get calculated in the setup code. So here we are, we're in the setup code, and you can see we have our compiler directive checking to see if 2-point calibration is on. If it is, just make sure that these 2 values aren't the same, and then it does that calculation to get the gain or the slope correction factor, right? The actuals divided by the measured. Then we can calculate our offset using the slope or gain correction factor, the measured value, and then the actual value. And then we say, hey, set this to true to let the user know and the software know that we did a 2-point calibration. And if you remember in the demo, this is what we printed out, showing the correction factors. Then if we go to our function that's inside the loop, this function handles the averages. It also then, if calibration is enabled, it applies the calibration correction factor right here, right? So we're returning the offset plus the gain or slope correction times the volts raw. Volts means the actual reading from the ADC before the correction. And then we return that as the measured voltage with our corrected voltage. Okay, that's it for using the 2-point calibration method to increase your ADC's measurement resolution. If you have any questions, please use the comment section. Thank you for watching.